Section 3.1 deals with inverse functions. So we actually talked about functions in the last review, and remember, a function is a rule of correspondence or an equation, right, is typically how we're going to define it, that assigns each element of A to exactly one element of B. And now we also say a one-to-one function is a function, so A has to go to exactly one element of B, but a function's one-to-one if it's also true that for every B you select, or every output, it only returns one element of A. So all one-to-one functions are going to be invertible. So we use the vertical line test to test whether a function or an equation or a graph is a function, right? So if we can draw a vertical line and kind of like slide it back and forth across the graph, as long as it only crosses the graph in exactly one point, we would say that this is a function. However, we have a similar test to determine if a function is one-to-one. So to be a function, it has to pass this test, but if it also passes the horizontal line test, meaning if I draw a horizontal line across the graph and slide it up and down, and it only crosses it in exactly one point, we know the function is one-to-one. And that's very important because all one-to-one functions are invertible. Inverse functions have the following properties. So the graph of the inverse should be the graph of the original function reflected over the line y equals x. So if you fold it over, you'll get the graph of the inverse. If you compose a function with its own inverse, it should just return x. So here, if you plug the function inside of the inverse, it should simplify to x. Or conversely, if I plug the inverse into the original function, it should simplify to x. The x and y coordinates on any point of x and y are reversed on f inverse. So when you reflect the graph over the line y equals x, you're actually trading the x and y values. So if a point 4, 3 is on the original graph, then that point moves to 3, 4 on the inverse. The domain is the range, and the range is the domain. So that's another thing that happens when we reflect over y equals x. We actually are trading all the x and y values, so it kind of makes sense that the domain and range should switch as well. Any one-to-one function you're guaranteed an inverse. However, functions that are not one-to-one may have inverses if we can restrict the domain of the original function to make it one-to-one. And so a great example of that is y equals x squared, and we're going to play with that a little bit during the review. If you want to find the inverse of a function algebraically, we write the original equation f of x as y equals whatever the equation is. Then we rewrite it where we take all the x's and replace them with y's, and all the y's and replace them with x's. So that is trading domain and ranges. Then we use algebra to solve the new equation for y, and if the new equation is also a function, it is the inverse of f of x. And we once again mentioned, note that you may have a domain restriction that might be required. So the first example says, well, let f of x be an invertible function. So we're telling you that this function is already invertible, and it says complete the following table. So we have a bunch of values of x and their corresponding y values that come out of f of x. So if I want to create a table for f inverse, well, knowing the properties we just went over, the x's and y's should switch. So if negative 2, 10 is on the graph of the original function, then 10, negative 2 should be on the inverse. So then it's 7, negative 1, 4, 0, 0, 1, negative 3, 4, negative 4, 5, and negative 7, 6. So all I did was flip the rows. Every xy became yx on the new graph.